Have you ever stopped to wonder how a super light aluminum car door gets attached to a high-strength steel frame? Or, how a jet engine actually holds itself together under all that incredible heat? Well, today, we're pulling back the curtain on the hidden science of joining materials that, really, were never meant to mix. This is the secret glue holding our entire modern world together.
All right, let's dive right in by just looking at the high-tech world all around us. You might be surprised to find out that it's built on some truly mind-bending combinations of materials.
It kind of sounds like the beginning of a riddle, doesn't it? One of them tears down the highway, the other one tears through the sky. But they share a deep, fundamental engineering secret. Any ideas what it is?
And that's it, right there. They aren't made of just one thing. Nope. They are carefully engineered hybrids combining things like steel, aluminum, titanium, and even composites, all to squeeze out the absolute best performance possible.
And look, this isn't some niche, abstract science. It is everywhere. In aerospace, it's all about making planes strong but also incredibly light. For the cars we drive, it's about safety and fuel efficiency. And in energy and electronics, it's about handling extreme temperatures and stopping corrosion in its tracks. These material mashups are all around us.
So, here's the crucial point. If you're going to build things with all these different materials, you've got to figure out a way to stick them together. And as it turns out, that is a whole lot harder than it sounds.
Okay, let's take a classic combo from the auto industry, steel and aluminum. You can't just weld them together the old-fashioned way. Just look at their melting points. Steel doesn't melt until about 1500 degrees Celsius, but aluminum turns into a liquid at just 660. So if you try to fuse them with heat, the aluminum literally becomes a puddle long before the steel even starts to think about getting soft.
So what actually happens at that boundary, that place where these two totally different worlds collide? What goes wrong when you just try to force it?
You get this, intermetallic compounds, or IMCs for short. Now think of it like this. You're trying to glue two really strong bricks together, but the glue itself dries into a fragile, crumbly layer of chalk. That's the IMC. It's this super thin, incredibly brittle layer that forms right at the joint, and it immediately becomes the single weakest point in the entire structure. It's basically the villain of our story.
Now here's where it gets really cool. Engineers have developed some absolutely ingenious ways to get around this problem. Let's start with the first family of solutions, which is, well, basically fighting fire with fire.
This is what most of us picture when we hear the word welding, right? Fusion welding uses an intense source of energy, like a powerful electric arc or a high-tech laser, to melt the very edges of the materials, letting them mix just enough to solidify into a single unified piece.
And the toolkit for this is seriously impressive. You've got your traditional gas arc welding, sure, but then you have these incredibly precise methods. Laser beam welding uses a super focused beam of light, and electron beam welding, which is often done in a vacuum, uses a literal stream of electrons. Both of them give engineers pinpoint control over the heat, which is key to minimizing those nasty IMCs. But what if you could join metals without melting them at all? Let's check out the second family of solutions, which takes a completely different path and relies on pure, raw force. This is solid-state welding. So instead of melting anything, these techniques use incredible pressure, intense friction, or even ultrasonic vibrations to force the atoms of the two materials to literally bond together while they're still solid. And the big advantage? No melting means a much lower risk of forming those brittle IMCs. A fantastic example is friction stir welding. Just imagine you have two strips of modeling clay laid out side by side. You take a spinning tool, you push it down right into the seam, and then you just drag it along the line. The tool creates so much friction that it softens the clay, or in this case, the metal, and it literally stirs and forges them together into a perfect bond. It's amazing.
And just like with fusion, there's a whole toolbox for this. Beyond friction stir welding, you've got ultrasonic welding, which uses high-frequency vibrations for delicate electronics. There's resistant spot welding. That's how most of the panels on your car are pinched together. And then you get into some even wilder methods like explosive bonding, which uses a controlled explosion to slam two metals together with so much force that they have no choice but to fuse.
Okay, so we have these two major toolkits, fire on one hand and force on the other. Now let's see how engineers actually pick the right tool for the job to build the things we use every single day. And this is where it all comes together. You can see the direct line between a specific problem and its unique solution. Need to join aluminum and steel for a car body?
Engineers will probably use resistant spot welding or a specialized hybrid laser weld. For a critical aerospace part made of titanium and steel, they might need the incredible precision of electron beam welding. Every single combination has its own tailored solution.
And this quote from the research really just hits the nail on the head. It's never about joining materials just for the fun of it. The choice is always driven by a specific need. Do you need the final product to be lighter, more resistant to rust, able to withstand the insane heat of a jet engine? The goal dictates the materials, and the materials dictate the joining method.
So here's the bottom line. Whether we're talking about fire or force, all of these advanced, incredible techniques have the exact same ultimate goal. It's all about controlling what happens at that microscopic boundary to stop or at least minimize our villain, those brittle intermetallic compounds.
And this chart shows you exactly why this is so important. A pour joint, one that's full of those chalky IMCs, is weak. It's going to fail. But as engineers use these techniques to get that IMC layer under control, to reduce it, the strength of the bond just skyrockets. Better control means a much stronger, more reliable product. End of story.
So it kind of leaves you with a fascinating thought, doesn't it? Maybe the next huge technological leap won't come from discovering some magical new wonder material. Maybe it'll come from figuring out an even better way to join the ones we already have. I mean, when you can perfectly combine the strength of steel with the lightness of a composite, what impossible things could we build next?